Anila ma'am?
Okay, ma'am. A very good morning to all the faculty members, our eminent speaker, Dr. Mithilesh Kumar, and dear participants. I welcome you all on session 1 or day 5 of AICTE ISTE 1 week online refresher program on artificial intelligence and cooperative Noma 5G network. I would like to welcome our eminent speaker, Dr. Mithilesh Kumar, professor from RTU Kota. It's my pleasure to introduce him. I welcome you, sir. Dr. Mithilesh Kumar received the BE degree in 1992 in Electronics and Communication Engineering from the Government of Engineering Kota, University of Rajasthan. MTech in 1999 in Communication and Radar Engineering and PhD in 2011 in RF Communication Engineering from Indian Institute of Technology, Delhi. His current research interests include RF communication, UWB active antenna, microstrip antenna, and microwave device designing technology. Dr. Mithilesh Kumar served as a lecturer from 1993 to 2000 and senior assistant professor from 2000 to 2008, associate professor from 2008 to 2013, and professor from 2013 to till date in electronics engineering department at Rajasthan Technical University, Kota. He has served as the principal of Government Engineering College, Halawad, and additional charge of Government Engineering College, Bara. He is the co-author of 183 research papers in referred journals, international and national conferences. He received first prize Best Student Paper Platinum Award in 2009 and IEEE International Conference on Antennas, Propagation and System in 2009 held at Malaysia from December 3 to 5, 2009. He has visited Malaysia, Japan, Germany. He is a member of the IEEE Microwave Theory, Techniques and Society. I welcome you, sir. Now I would like to invite Dr. Mithilesh Kumar to deliver his talk.
Thank you for nice
Welcome
presentation.
you, sir.
So, इसमें पीपीटी शेयर करने का कहाँ पे आएगा?
सर माइक के पास में ऊपर एरो आ रहा होगा।
हाँ हाँ आ रहा है
जी।
So my content is visible or not?
Yes, sir, it is visible.
So I think it is better visible.
Yes, sir.
So can we start?
Yes, sir.
First, I would like to thanks to all of you. That's you people have invited me to deliver a talk on this program. Today, I will deliver the basic antenna design. and that's antenna is for the 5G. So all of we are aware that is the 1G, 2G, 3G, 4G, 5G, and all these are the basically part of communication. I think I have to start from the basic, because some people may be aware about the communication, some may not be. An antenna is the one of the key element for the wireless systems. So later on I will discuss this. So first, communication technology. Communication system can be a wired or wireless, and the medium used for the communication can be a guided or unguided. So earlier there is a wire system. Nowadays the wire system is replaced by a wireless system. In wire communication, the medium is a physical path like a coaxial cable, twisted pair, cable, optical fiber. You people have seen everywhere. Then wireless communications was started in 1960s, and wireless communication does not require any physical medium, but propagate the signal through space. So the transmission and reception of the signals is accomplished by the antenna. Antenna are electrical devices that transport the electrical signal to radio signal in the form of electromagnetic wave and vice versa. So now you people have already know that is the electromagnetic wave was invented by the Maxwell mathematically. Then practically is what proved by the Hertz and the Marconi and Jesse Bose. And these EM waves propagate through the space. So both transmitter and receiver consist of an antenna. So without the antenna, there is no wireless communication. So now this is the one of the important element. So now you design for the 1G, 2G, 4G or whatever. The engineer should know how we transmit the signal. So antenna is the one of the important device. Without antenna, nothing is possible. So model of general communication system, there is a transmitter and receiver is there. In our mobile handset also, the mobile is also work as a transmitter as well as receiver. In between there is a channel path, noise and all these. So the transmitter whose primary task is to group the digital data stream into a symbols. To map these symbols onto analog waveform, then to transmit to the air through an antenna. And channel which represent the effect of traveling through space including reflection, distortions, edge electromagnetic pulses impinging on the other object. So now about these reflections and all these, I think you people have studied some talks related to the MIMO and other things. So the receiver which collect the electromagnetic energy from the antenna take the extremely weak signals. So again we have to reconstruct the pulse shape and map it to the appropriate symbols and then to the binary bit string. So large of the data processing and other things is required. So here my task is related to only internet design. So now before to design any communication system like 2G, 1G, 4G. So now there is a radio spectrum is there. So according to the spectrum, we have to design the system. Earlier we people are using the radio, then remote control, TV, cell phone, GPS, medical, Wi-Fi. Presently my mobile is, laptop is also connected to the Wi-Fi. So microwave pager, satellite, cordless phones, walkie-talkies. So everywhere we are using the electromagnetic spectrum. And now this spectrum is fixed for a particular applications. So whenever we design any device, first we should know the specification of the spectrum. So which spectrum will be useful for a particular applications. So now come to the wireless communication. So all of you, I think most of the people is already know that is a terrestrial mobile telephony. Already you have a mobile in your pocket. Earlier the mobile was working in 0.8 to 1 gigahertz. GSM, global system for mobile communication. Then personal communication system, PCS, work on the 0.9 to 2.2 gigahertz. And then the cellular telephone and paging. Earlier there is a pager is came in the market, then the pager was gone, and then your mobile is came into the market. And similarly, there is a satellite communication 1 to 6 gigahertz and 12 to 14 gigahertz. So multimedia broadcasting, handheld devices and data communication. Wireless LAN, presently we are using. Everywhere is the wireless, there is a Wi-Fi and all these. So now these are working on 2.4, 2.8 gigahertz and 5.7 to 5.8 gigahertz. So as we already know, that is just like your Geo Fiber and other, they use the two connections actually. One is work on the 2.4 to 2.8 gigahertz and other work on the 0.57 to 5.8 gigahertz. So now here, when the frequency will be very high, then your data speed will be high. So here naturally, so now there's a this 5.7 to 5.8 gigahertz working system will be better than to the 2.4 to 2.8 gigahertz. The same thing is happens with the your 1G, 2G, 3G, 4G, because the day by day there is a frequency is going to increase. Later on I will discuss the communication between the computers, between buildings and within a building. So everywhere we have a wireless nowadays. So wire system is gone. So now here that's a mobile telephony, because now just I will discuss the 5G in coming day. So here that's the 1G mobile telephony came in the first generation, that is the analog to digital communication. Then second generation mobile telephony came, that the speed of kbps is increased into the mbps. Then 3G mobile data, then mbps to the gps. So now you people have seen the difference when the 2Gs came, then our mobile having the only data communication and your voice communication. But when 3G came, then in the video calling is there, extra feature was added, because now their speed is increased mbps to gbps. And now here 4G mobile broadband, then we have increased again speed and 5G mobile everything, because of internet of thing and all these. So when we integrate the all things through a remote or with the mobiles operation or internet, then we require a huge data, and then our bandwidth should be very large. So now here that's a mobile telephony, 5G wireless. On the other hand, is expected to operate in different bands depending on the application and performance requirement. So now here the evolution of the wireless technology, and this technology is always based on the frequency, operating frequency, and the bandwidth. So bandwidth is a very important for any device designing actually, because you already know in the Shannon theorem that is a channel capacity is directly proportional to the bandwidth. C is equal to delta B log 1 plus SYN. So S we cannot increase too much, so C is directly proportional to delta B. So bandwidth can be easily increased by the increasing the operating frequency. Otherwise we have to use so many techniques to increase the bandwidth. So now here that is the in the 1G, that is a 30 kilohertz is the bandwidth. Operating frequency is 800 megahertz. Similarly in GSM, that is a 2G, 200 kilohertz bandwidth, 800 to 1900 megahertz. Then 3G came 5 megahertz bandwidth, and 800 to 2100 megahertz, 2.1 gigahertz basically. Then 4G came 20 megahertz. So definitely presently we are using 4G, because in some country there is a 5G scheme, but in India there is in trial phase. So now here 800 to 22.1 gigahertz, and then 5G schemes nowadays, that is the 400 to the 2000 megahertz, this is the bandwidth, and the 500 megahertz to 40 or even 100 megahertz, 100 gigahertz. So now here the whatever communication nowadays we have, the all are working on the gigahertz, and gigahertz device designing is very difficult, because size of the component is comparable to the wavelength, and wavelength becomes very small. So device size becomes so small, and we have to design be carefully. So that's why the hardware designing of this level is very difficult. In case of the 5G, because this 5G is working on the 28, 30 gigahertz and even though 100 gigahertz also. So now here this is the 5G spectrum. So now here that's the existing mobile spectrum is working below 1 gigahertz or 1 to 6 gigahertz. So this is the existing mobile 1 to 6 gigahertz, and there is a new mobile spectrum is came from 30 to 100 gigahertz. So now here you can see with the help of this diagram, that is earlier was the we have in city there are when there we have a 2G, then there is a I think in small cities there is a very big size of the cells, but then when this frequency increases, then the cell is divided into the micro and small cells, and when this 5G will come, then your antenna will be placed within 100 meter or like that. So now everywhere will be the antenna, and the big network will be installed actually. So large number of communication engineers is required for installations and their configuration purpose and all these. So here there is a fixed links and the satellite and the small cells. So there will be a huge number of the stations will be placed in our city to install the 5G network. So when all these things will be installed, then what happened? Everything will be connected to each other. Well, our city becomes small, just like with the help of this diagram. each and everything we can connect it. Just like a vehicle tracking, smart vehicles, equipment monitoring, machinery tracking, irrigation management, and livestock tracking, access control. Because everything will be connected to each other. Nowadays, there are so many machines which came into the market. They can easily control with the help of the internet or your mobile also. That is a smart or intelligent devices came into that. So when in our house or everywhere, all things will be integrated together, then we require a huge bandwidth. Then this 5G network architecture will complete this requirement. So now here we need a central server, then there will be 5G small cells and micro cells, local server, and the existing system will also integrate to the 5G because we cannot remove the 4G and 3G also. So now the all integration will be there. 5G architecture, 5G micro, 5G small cells, and all these. So here, that is the integration will be there with the help of the 5G, 4G, 3G. So then each and everything will be connected to the each other. Or we can say now there is everything will be automatized and the people life becomes so easy actually. So now here, this is the basic idea about that why we require a 5G, because 5G give a very huge speed and because we require a large data. So now this 5G or 6G will give the fulfill this requirement. So now here the antenna is the one of the important part. So here first I will discuss about the basic antennas. Then we will discuss the design of the antenna. Then we will discuss the design of the 5G antenna. So antenna are essential part of any wireless system. According to the IEEE standard definitions of terms of antenna, an antenna is defined as a means for radiating and receiving radio waves. So now here in our mobile system also we have a one antenna that is used for the transmitting as well as for the receiving purpose. So antenna is an electrical conductor or a system of conductor. So now here for transmission, radiate electromagnetic energy into the space, and the reverse of that in the reception collect the electromagnetic energy from the space. It means around us everywhere we have electromagnetic waves having a different electromagnetic spectrum. So when that's our device will sense, then we'll get the signals. In two-way communications, the same antenna can be used for transmission and reception. It means there is only one antenna is required for the transmitting and receiving. For this, there is just here is the very brief history of the antenna. So Maxwell equation was started in 1864. Then there is electromagnetic waves was invented, and Hertz in 1888 that is invented parabolic metal cylindrical antenna. Then Marconi has done the communication systems. Then World War II, we have used the radars and each and everything on that time. So there is a radiating aperture, reflectors and arrays was invented. Then later on there is a for the analysis purpose in 1960 Harry Anderson invented the method of moments. Then later on then 74 to 81 uniform geometrical theory of diffraction. So there are so many theories is available nowadays. So then we can analyze the antennas. So sometime what happened by using the existing formulas and all these we can design the antenna. Sometime we start with the help of the structure, then we do the reverse of that. Then we try to find out the equivalent circuits and all these, and then we have to analyze this. So now here with the help of these methods, now there is a people have invented your simulation software because in the earlier on that time. So now we have to design the antenna and by making the calculations with the help of the pen and pencil and calculators. So the life was so difficult on that time. So now here the antenna is a circuit element that provides a transition from a guided wave on a transmission line to a free space, and it provides for the collection of electromagnetic energy. So now here why it's written actually free space impedance you know that is 125 and 377 ohm. So now when this antenna radiations will not be matched to that, then antenna will not deliver the energy to the free space. Otherwise it will itself collect the energy and now it will not radiate. So that's why the radiation characteristics is very important for the antenna. So in transmit system, the RF signal is generated, amplified, modulated, and applied to the antenna. So before that, now we have to process these things. In the receiving system, again, collect the electromagnetic waves, and there are cutting through the antenna, and include the alternating current that are used by the receiver. So here we have a very beautiful property of the antenna, that is the reciprocity. The same antenna can be used for the transmitter and receiver. So an antenna ability to transfer energy from the atmosphere to its receiver with the same efficiency with which is transfer energy from the transmitter into the atmosphere. So antenna characteristics are essentially the same regardless of whether an antenna is sending or receiving electromagnetic energy. So again, there is another property, there is a polarization. So polarization is the direction of electric field, is the same as the physical altitude of the antenna. A vertical antenna will transmit a vertical polarized wave, and horizontal antenna will transmit a horizontal polarized. So now here, to the receive and transmit antenna need to possess the same polarization. If the polarization will be opposite, then what happened? The signal will be in opposite phase and will not get any signal. So now this is again one of the important properties, because what happens, so now when we put a large number of antennas, so now there will be a signal will be go from the multi-part directions, and there are so many problems arises. So now this all things you people have to know about this. So now here this is a basic antenna concept. So the antenna is a region of a transition between a wave guided by a transmission line and a free space wave. Transmission line conductor separation is a small fraction of a wavelength, while separation at the open end of the transition region or an or antenna may be many wavelengths. So now here this is the generator or transmitter. This is a transmission line. So now here after this transmission line we have to connect it to the antenna. But nowadays now we are using the active antenna, so we do not require this transmission line and we can save our energy and the losses also. So now here this a flat transition region of the antenna, and now the free space the radiating in a 3 dimensions. So electromagnetic wave will be detached and then now it will transmit to the free space. So antenna radiate the or receive energy, transmission line guided. Why does antenna radiates? Because now these questions came in the mind most of the time. So why it radiates? If the charge is moving with a uniform velocity, so there is a radiations. If the wire is curved or bent or discontinuous, terminated or truncated. If the charge is oscillating in a time motion, it radiates even if the wire is straight, because earlier we are using the wire antenna. So now here this one of the important property is the oscillating. It means the RF signal will be transmitted. So here there is a types of antenna. So large number of antenna is there. So now we can design any kind of according to our requirement. So here that is the to design any antenna, then the one of the basic antenna, that is the isotropic antenna, idealized, radiate power equally in the all directions. So with the help of that we will decide the directivity and all these. So later on I will discuss. And then the dipole antenna, half wave dipole antenna or Hertz antenna, because now this was earlier invented by the Marconi, and the quarter wave vertical antenna was invented by Marconi antenna. So the scientists having their name, Hertz antenna, Marconi antenna and all these. Parabolic reflector antenna, already we have in our rooftop for TV purpose. So now everywhere you have seen the parabolic reflective antenna. So here this is a basic antenna parameters, because when we design anything we should know the parameter. So now here these parameters is classified into the 3 categories. One is the circuit quantities in between transition region, then there is a space quantity. And so now in circuit quantities there is the input resistance, input impedance, noise temperatures, and then current distribution. So in the transition region, so there is current distribution we have to know. In a space quantities, we should know radiation pattern, power density, half power beamwidth, directivity, gain, effective aperture, radiated power, and polarizations. So now you people have to know the definitions and what are the significance and what is the physical significance of these. Now you should know before to design the antenna. Then the bandwidth, efficiency, complex equivalent length. So now to analyze this antenna, then we need all these parameters. So according to that, we decide the antenna will be useful for a particular applications or not. So before design or before process to design any antenna, we should know what is the objective, what is the purpose, what is the operating frequency, and according to our requirement, which parameter will be suitable. So according to that, we have to decide that. So antenna with the communication system. So now the transmitter cable, antenna, free space. So now here in between there is a tree, buildings and all these. So according to that, we have to design the MNIT systems and all these, because now we have to minimize the losses, and then there is a receiving antenna, then through cables or so we receive the signals. So antenna with a communication system in an advanced wireless system, an antenna is a usual required to optimize or accumulate the radiation energy in some directions and suppress it in other at a certain frequency. A good design of antenna can relax system requirement, improve overall system performance. Your antenna will be poor, then what happened? Poorly radiated and poorly receive the signal. So now the whole performance will be go down. So to describe the performance of an antenna, there are several commonly used antenna parameters, including the impedance bandwidth, radiation pattern, directivity gain, efficiency, and polarization. So when we read any papers or any book, so now these are the basic parameters. So everywhere we have to measure these parameters. The antenna applications. So whenever we are using the wireless systems, everywhere we use the antenna. So ground-based telecommunication system for direct broadcasting, radio link. You have seen in the our railway stations where there is a microwave link is there, because our earth is having a curvature. So after 45 kilometers, now we have to place the another link setup. So there is a mobile phone and base station, traffic toll. Nowadays we are using RFID tag in our car. So now just we pass the traffic toll and automatically the money is detected. Navigation. So now here in mobile also there is everything you get the information. So satellite communication systems linking ground-based systems at the long distance. Satellite TV, mobile earth terminal and mobile phone. So now in coming days now you people can see in the satellite mobile phone will came into the market also. So now here civilian and military radars, weather radar. So now in our mobile we see now there is a 2 days the forecast. So now there is a in our mobile also there is a written in quota, there is a clear 22 degree centigrade temperature, air quality index 108. So now all these things is possible with the help of this. So weather radar and another is the air traffic radar. So you have seen also military search and scouting radar, synthesis aperture surveillance radar, pollution, traffic, fishing borders, ionospheric and planetary research. Radiometry, military early warning system, radio astronomy, meteorology and land resources surveillance. So here there are various types of the antenna. People have invented a huge number of the antennas. So now here the name, according to the name, there is a dipole antenna, folded dipole, monopole, loop. Loop means the structure in form of a loop. Helical structure will be there. Then there is a helical antenna, turnstile. Then your turnstile antenna, disc in form of disc. Now there is called the disc antenna. Yagi-Uda antenna, parasitic arrays. Earlier, I think you people have seen for the TV reception before the dish size came. So when we see the Doordarshans and all these, so now there's a in our home we are using the Yagi-Uda antenna. And then there is a phased array. Nowadays, now we are using the Microsd antenna. That becomes very small in size and all these. RFID tag already you have put in your car window screen. RFID tag antennas. And recently that we are using the UWB antennas. Then wearable technologies came also, because for a specific purpose we use this wearable antennas. Then there is a smart antenna. Automatically now it will adjust beamforming and all these. That's your smart antenna by using the artificial intelligence, whatever you discuss in this course. So now here most of the time we use the smart antenna. So now here these are the basic classifications. Another classification is the electrically small antenna. Resonant antenna. Resonant means now the antenna will resonate in a particular frequency. Now suppose for a fractional bandwidth is very small, then there is a we say now there is a resonant antenna. If the antenna is working on 3 gigahertz, so then percentage bandwidth less than 10%, then we can say now there is an antenna is working as a resonant antenna. Broadband antenna means now the antenna is work from the 3 to 5 gigahertz. It means the same antenna used for the 3 to 5 gigahertz, very large range. So then there will be broadband antenna. And then aperture antenna, then array antenna, because single antenna is not sufficient to transmit the energy. So now that's why we require the array of the antennas. So now there is 1000 microstrip antenna, 2 lakhs antenna, because suppose we want to transmit the signal to a moon or very far, so then we require a large number of antenna. So now here this is the basic horn antenna, because for any test setup and for measurement purpose radiations and all these, so we require E plane, H plane and pyramidal horn. So when you see the NQ chamber, so now at the receiving side, now you will see the horn antenna. So you people have to be familiar about the horn antenna, because according to that we have to decide the E plane, H plane and all these. So now here excitation is the TE10 mode. So now you should know what is the TE10, and then impedance matching through a flare. Why this impedance matching is important? Because the impedance matching will not be there, then your signal will not be passed. To transfer the maximum power, there is a matching is required everywhere. So gradual transmission with a minimized reflection, because our return loss should be minimum, because we want to do the most of the power should be radiated. So now here this is a slot on a waveguide walls. So radiation is a maximum at maximal interrupted current. So now here the radiations, here there is no radiations because they are in opposite page. So now here these are the basic patch structures. So I think you people have already seen the patch antenna. Patch antenna is designed on the dielectric substrate. If not seen, so then you can, in our mobile we are also using the patch antenna. So here this is the this patch antenna or microstrip antenna is the design with the help of the MIC circuit, microwave integrated circuit. So MIC is a planar construction in which all circuit components are attached together. So what happened actually now there is a PCB, that's not a PCB, basically a dielectric substrate. So on the dielectric substrate now the same antenna and other transmitter components can be designed. So the circuit components are produced by the same technology, manufacturing process on low dielectric support. So with the help of the dielectric substrate, if you design the whole component, that is called the MIC. If the MIC, if this dielectric substrate is replaced by a gallium arsenide, or we can say semiconductor substrates, then this MIC component convert into the MMIC. So now definitely their size becomes so small, very small. So now here in our mobile we are using the MIC as well as MMIC, and then the MEMS technology, because for some devices are designed with the help of the MEMS, some component is designed with the MMICs and some is with the MICs. So now here just I am giving a brief idea what are the planar transmission lines. The circuit are built using the planar transmission line. There is a strip line, microstrip line, suspended substrate line, slot line, coplanar waveguide, coplanar strip. So before design any antenna, you should be familiar about these transmission line, because now these transmission line having the different properties. So now here, according to your specification purpose, according to your specs, you have to choose the which transmission line will be suitable for the design of the antenna. So most of the time we design the antenna with the help of the microstrip. So now there is an antenna name is the microstrip or printed antenna. However, that is a coplanar slot lines. These are also used, strip line and suspended also, because now just we have to increase the radiation efficiency of these. So they have different benefits, merits and demerits. So now before proceed to design, you people be familiar about these. Then come to the how many types of the substrate. Substrate is the technical name basically. Just you most of the people have seen the PCB, but in case of the PCB, now there is a PCB structure, and the top and the bottom there is a copper is there, in between dielectric is there. But now there is a PCB uh, rate is very small. That's just like a 50 to 100 rupees. Now you people can get. Why? Because now, and these PCBs can be used for the low frequencies. Low frequency means now in kilohertz and up to the megahertz. But now here these old devices are designed in the gigahertz. So in the gigahertz, what happened? There is a size of the component is comparable to the wavelength. Wavelength means now there is your lambda g is equal to lambda naught upon root epsilon r. So epsilon r is the dielectric constant, and this dielectric constant play a very important role to design the devices. So now here if epsilon r is varied, then our circuit design becomes failure. So here the normal PCB cannot be used for the designing for the high frequency devices. So now here we have a different type of the substrate. There is a plastic, PTERT duroids, FR4, ceramic substrate, ferrite and garnet, sapphire and semiconductor substrate. So before proceed to design, you have to first procure the substrate, because sometimes the people download the papers and they start the designing of the antennas, and then later on they know that the substrate is not available and substrate cost is very high. So what happened? The all design is becomes useless, because you cannot fabricate. Because one time what happened, when I was doing my PhD at the IIT Delhi, so then one lady came and she has designed the filter on the sapphire, and sapphire is very costly substrate. Nobody can bear the cost, so definitely she has to change the design on the another substrate, right? So first you have to procure the material and then start the designing. Then another is the circuit technology, lumped element MIC, distributed circuit MIC. So you people should know how we convert these components lumped into the distributed and distributed into the lumped elements. Otherwise, we have to integrate so many components. Now, suppose filter is there, so then you have to place the LC. But now, with the help of the distributed circuit, so now we can print the all component in a single chip. So here, this is the structure of the different planar transmission line. So now here, this is the strip line. There is a we have two ground, upper and bottom. In between, there is a conducting strip is there. Microstrip line is open structure. This is the ground. This is the top structure. So here it can easily radiate. This is a slot line. So it design used for the slot antenna also. Coplanar waveguide, coplanar antennas, and coplanar strip. So all these are used for the designing purpose for the different applications. So here these are the various planar transmission line structures. So you people have to go in a detail. Then this suspended microstrip line. So now here suspended strip, that is a way to introduce the air gap. By introducing this air gap, what happened? So now here there is a electric field passes through the two mediums. So now here just we have increased this height. So when this height of the substrate is increased, then the epsilon R effective will be decreased. So by decreasing this dielectric constant, so now there is a dielectric losses will be decreased and our radiation efficiency will be increased. Similarly, inverted microstrip, sometime we design a filters and all these, so now we use the inverted microstrip. Then there is a suspended strip line also. So here these are the quasi TM mode actually. You already know that is a coaxial cable having the TM mode, and this is almost similar to that. So now the people have given the name quasi TM. So in microstrip, inverted microstrip, coplanar waveguide, trapped inverted microstrip, suspended strip line, we have a quasi TM mode. And now these are the image line, fill lines, slot lines used for the 100 gigahertz and all these. So now these are the completely non-TM modes. So now you people be familiar about these transmission lines, because according to that we have to choose the design, which design will be suitable for our antenna design or any component. Then come to the fabrication technology for MICs. Because here we have a large number of fabrication technology. One is the simple fit photolithography process. So I think in our first year engineering, or you already have available in our laboratory also. Then there is a thin film technology, thick film technology, combine the thin film and semiconductor growth technology. Then semiconductor technology, I have already told you that is if the dielectric substrate will be replaced by a semiconductor, then it convert into the MMIC, and definitely the size becomes so small. So here this is simple photolithography. So according to the photoresist material, we have to prepare the mask, maybe a positive or negative, depends on the photoresist material. So here this is a very simple technology. So now first we bring the substrate and we cut the substrate, then we clean the substrate, and after cleaning from the copper, then we have to put the photoresist material, then we have to put into the oven, then it will be hard, then we put the mask, then it will go inside the UV, ultraviolet section. So now here what happened? So the mask with the help of the ultraviolet light, so now it will be exposed where the open area is there. Then we will remove the mask and then expose the photoresist removed by the developer action. So softboard after etching, copper removed from the top surface, asset where they protected. Now in case of a microstrip antenna, the bottom side, the ground side, we have to protect it. and the top side unwanted copper we have to remove. So now we have to dip in the ferric chloride. I think you have done this in our lab also. So in your laboratory. So now the finally your device will be ready. So now the finish surfaced with a solvent having removed all unexposed photoresist. So finally your device is ready. So now here to design any kind of antenna, 5G, 4G, 3G, whatever. First you people have to know the how we design the basic microstrip antenna. So now here if you know the basic microstrip antenna designing, then you can design any antenna. So here the microstrip antenna. So already I have discussed the microstrip. So what is the microstrip antenna? That is the microstrip plus antenna. It means with the help of the microstrip we design the antenna. So microstrip, the most popular type of planar transmission line used to efficiently carry energy between 2 points. So now here this is a ground, this is epsilon r, then this is top is the radiating copper. So now here we have a width, height of this, because now these are the specifications. So height of the substrate is the h, and this is the dielectric constant is a epsilon r. This is the conducting strip, the black strip, and there is the width. And this width is vary according to the impedance. If your impedance will be very high, then what happened? The small will be, width will be small. If the impedance is small, then your width will be very high. So here microstrip patch antenna consists of a conducting patch. So now here this is a certain nomenclature because some may be knowing, some may not be. So now here this is the patch. So this is a radiating patch, and this is substrate, and this is ground plane, and now here this is a feed line. So here we have to feed with the microstrip line or different feeding methods. Later on I will discuss. Feed line is very important. So before feed line you should know what is your system impedance. Most of the time the system impedance we take 50 ohm. Why we take the 50 ohm? Because most of the measuring devices having the port impedance is a 50 ohm. But sometimes for any specific purpose now people can use 75, 100, whatever needed. So according to that you have to design. So here the microstrip patch antenna consists of a conducting patch of any planar or non-planar geometry on one of the dielectric substrate with a ground plane on the other side. So microstrip discontinuities can be used to the advantage. So an antenna is made from the patch of conducting material on a dielectric substrate above ground plane. So now here this is the rectangular microstrip patch antenna feed by a microstrip line. So here this is the 3D view, and now this is the actual fabricated antenna. This is a copper. So now this is a feed line. This is a quarter wave transformer is there for the matching purpose. So here definitely this antenna have a certain advantage and disadvantage. So now here advantage is small size, low cost and weight because it's very small weight. Ease of installation does not give a rise to aerodynamic drag when used in craft. Low profile antenna can be easily mounted to a metallic conductor or other surfaces. No space for feed line is required. The feed line can be placed behind the ground plane. Compatible with MMIC design, I have already discussed, because the whole component will be, when we choose a gallium arsenide substrates, then the whole component will be fabricated in a single chip. That is a monolithic micro-integrated circuit. Monolithic means, mono means one, lithium means one single stone. So now everything will be fabricated in a single chip, just like your IC fabric. So definitely when you open your mobile, so then you will get only one IC there. So they allow the use of additional tuning element like pin or varactor diode between the patch and the ground plane. Suppose you are using the tuning of these. So now these are the different antenna, tunable antenna, all these, so you could design it. It has a certain disadvantage also, low efficiency, because single pouch antennas cannot radiate too much. So we require a array of the antenna. A small bandwidth, typically a few percent, less than 4% or 7%. So here low gain, low power handling capability. So for high power purpose, we use a horn antenna, dish antenna, and all these. So here the shape of a patch antenna. So you can design in any shape: circular, square, elliptical, rectangular, triangular, diamond shape, disc, sector, and circular ring also. So generally, this microstrip antenna are a thin metallic patch of various shape, etched on a dielectric substrate of a thickness h, usually in the form of 0.003 lambda naught to 0.05 lambda naught. The substrate is usually grounded at the opposite side. So here we have a two radiating slots. This is radiating slot 1, this is radiating slot 2. Already have a, these are the another slots, but they are opposite to each other, so their phase will be opposite phase, so now the radiation will be cancelled out. So in case of the microstrip antenna, there is a 2 is the radiating slot. Now the one is this and another is this. So this is the rectangular patch antenna. This is the circular microstrip antenna. In case of a circular, now just we feed through a coaxial connector also. We can feed microstrip also. So now here with the help of these electrical field lines. So now just by doing this now due to the fringing effect. So here this physical length is L, but now electrical length will be slightly greater than to this. So now definitely it will affect our design. So now we have to make a certain correction. So later on when I will show you design, so now that correction will be made due to this fringing effect, right? So the dimension of the page are usually in the range from lambda naught by 3 to lambda naught by 2. The dielectric constant of a substrate epsilon r is usually in the range from 2.2 to 12. The most common design use relatively thick substrate with a lower epsilon r because they provide better efficiency and larger bandwidth. On the other hand, this implies larger dimension of the antenna. The choice of the substrate is very much limited by the microcircuit coupled to the antenna, which has to be built on the same board. The microcircuit together with the antenna is usually manufactured by photo etching technology. I have already discussed photolithography process. They are one of the cheapest process. But nowadays there is a PCB fabrication machines is there. In the recently in our RTU we have also purchased. The cost is around 30 lakhs. So now here we can just make some program in a server files and all these, and then we give the data. Then automatically the machine will fabricate your antenna. So now here this is single slot radiator. This is a narrow slot. This is circular ring slot, white slot, circular page. So the feeding microstrip basis line is a beneath H on the other side of the substrate. So now here the transmission line in the opposite side and slot in the another side. So depends on our requirements. So we design different. So this is a microstrip traveling wave antennas. There is a combo microstrip traveling wave antenna. This is a meander line microstrip traveling wave antenna. This is a rectangular loop microstrip traveling wave antenna. This is a frank line. So here, according to our requirement, now we design the antenna. This is the microstrip antenna array. So now here one antenna I have already told that is a one antenna do not give a sufficient energy for the transmission purpose. So now just we require a more than one antenna. So now here as a RF engineer, you people have to know how we design this feed network. So here this is another task. So now here this is a 50 ohm line. So here this again we have to divide the power and the same power should be go there. So now you should know how we design the power divider. So now here this is a 4. How many power divider is there? 1, 2, 3, 4, 5, 6. So now here this energy is divided into 6 again in the 2 and then 2. So now the power should be reached in the same phase according to our requirement. So now you should know how we design this, right? So here this is a feeding method. And microstrip antenna is a most popular feeding method is 4 types. The first is the microstrip feed. So this is the microstrip line, and we connect a patch. So easy to fabricate, simple to match by controlling the inset positions. So now here this is a 50 ohm line. Actually, what happened? This is in a patch. And a patch has a different impedances. In the outside there is a impedance is very high, and in the center there is impedance is very low. So here we have to match this because now our line is 50 ohm. So now here it will be inserted up to the level where the impedance is 50 ohm. So this is the meaning of this. So by controlling the inset positions, so we have to match it. And relatively simple to model. However, as the substrate thickness increases, surface wave and spurious feed radiation is increases. So here we have to think all these parameters. And another is the coaxial profit. Coaxial profit means you people have seen the probe also. So just we have to make a hole and we have to insert that. So here this is your substrate. So we have to make a hole from the bottom side. We have to connect this coaxial connector. So here easy to fabricate, low spurious radiation, difficult to model accurately, narrow bandwidth of impedance matching. And these are the two coupling, another aperture coupling and proximity coupling. Here there is no contact. No contact means your transmission line is from the other side and your pH in the another side. Because sometimes we do not require the contact, but how they are connected? They are connected electrically. So Microsd feed lines and a radiating patch on this both side of the ground plane. The coupling aperture is in the ground plane. So low spurious radiation, easy to model, difficult to match, and narrow bandwidth. Proximity coupling, again this is there is no contact. So Microsd feed line and radiating patch are on the same side of the ground plane. So largest bandwidth. If you want to increase the bandwidth, then we have to use this coupling. Otherwise, in microstrip coupling, there is a percentage bandwidth is I think around 4 or less than 4% bandwidth. So we have to increase the bandwidth because bandwidth is play a very important role nowadays actually. That's why we require a UWB antenna and all these. They give the huge bandwidth because nowadays we require a huge data, right, and speed also. So relatively simple to a model has a low spurious radiations. So here these are the more example of microstrip and coaxial profit. So now different structures, rectangular, circular, triangular, whatever you needed, right? So here the first questions came into the mind because I have told you so many substrate FR4, RT, Duroid, right? So now first we have to, there is a criteria for a substrate selection. Which substrate will be suitable for my designing actually? Depends on your pocket and cost and all these. Other is the availability of the materials and there is a, these are the certain requirements. So now here possibility of a surface wave excitation. It should be minimized. Effect of the dispersion on a dielectric constant in low tangent of the substrate, then the losses will be minimum. So magnitude of the copper loss and dielectric loss and isotropy in the substrate. Effect of temperature, humidity and aging because our temperature is also vary. So now it should not affect the characteristics of the substrate. Mechanical requirement, there is a conformability, machinability, solderability, weight and elasticity. And finally is the cost. Because for any designing, the cost is important. Now which engineer will be the best engineer? Who give a cheapest one, right? So here this is the suspended patch antenna when we introduce the air gap because this is the housing. So where this is the top of the substrate. So now just we put on that and we introduce the air gap. By introducing this air gap, the dielectric constant and effective dielectric constant will be reduced and definitely the dielectric losses will be decreased and the radiation efficiency is increases. So now here advantage of a suspended patch. So very low conductor loss because of the introduction of the air gap. Provide the flexibility to tune the resonant frequency of the antenna by varying the air gap. So now here this is the air gap. Na? So if we put a screw or a mechanical tuning, so now this air gap suppose 0.1 to 0.5 we can vary. So definitely their epsilon r will be vary. And you already know the lambda is equal to lambda naught upon root epsilon r. So when epsilon r will be vary, the lambda will vary, then frequency will be vary. So now here they provide a flexibility to tune the resonant frequencies of the antenna by varying the air gap. Offers increased bandwidth as a result of increase in the height of the dielectric region below the patch and the lower effective permittivity. So now here it has again same applications in airborne systems such as aircraft, missiles, rockets, satellite, in communication system for direct broadcast, satellite reception and data transmission, radar altimeter antenna for communication between satellite, mobile and satellite imaging systems, electronic warfare, smart weapon, modern GPS in biomedical system. So now here question is comes how we design these antennas. So now here these are the certain design equations parameters. So those people are not familiar, so they can go through a book or maybe note down. That is the antenna design antenna book that is by the C.A. Balanis. So that is in the chapter 14. So now they have given a very beautiful designing. So now just with the help of these formulas and derivation is there also. So now you people can refer that book and you read the chapter number 14. Be carefully. Otherwise you can refer another books also. Microscope and printed antenna designed by the Randy Bancrofts. There are so many books is available. So now here these formulas is available everywhere, but you should know the procedure. So now here before designing, so now there is a specific design frequency is there, substrate thickness is there, dielectric constant of the substrate and size of the substrate. So here design frequency, now we are designing for the antenna for the 5G. So now once again I roll back to 5G, 4G. So now here this we have discussed earlier. Na? Let's say UC. This is the frequency, right? So existing system is 1 gigahertz, 1 to 6 gigahertz. Now there is a 30 gigahertz to 100 gigahertz. Now suppose I want to design the 30 gigahertz. The same formula will be used. You want to design on the 1 gigahertz. Again same formula will be used. According to that you have to choose the structures and all these, right? So the same formula will be used for the 5G, 4G, 3G, 2G, whatever you require, right? So now you people have to know how we design the antenna, right? So design frequency, here we are talking about the 5G. So now your design frequency will be according to the 5G spectrum. Then substrate thickness, because whatever substrate is available in the market. So now if you are using the gigahertz, higher frequencies, then you have to choose the substrate accordingly, because your FR4 is normal substrate, na? That's the cheapest one. It will not work for the 30 and 35 gigahertz. It's difficult. Similarly, connector is again problem, create a problem above 35 gigahertz, because there is a millimeter wave design is there. So now this their component is again costly. So now each and everything you should know actually. So the substrate thickness, dielectric constant of the substrate, and size of the substrate. So definitely the frequency is increased 30 gigahertz, the size becomes so small actually, right? So when the size becomes so small, so difficult to solder, difficult to connect. So this problem is arises actually. So here, just these are the design formula, and this design formula is applicable for the all frequencies, 1 gigahertz, 4 gigahertz, 3 gigahertz, 100 gigahertz, whatever. So now this is the basic for you people. So now you start the 5G antenna. First you have to design the 5G antenna for microstrip, simple microstrip antenna, right? By choosing your frequency 28 gigahertz suppose. So now just you to take 28 gigahertz here, then you put the substrate values, and with the help of these formulas you calculate the dimension of L and W. So now here the length and width we have to calculate. So before proceed to this, now here first we will calculate the W, width. So width can be calculated by using this formula, that is 1 upon 2 FR mu naught epsilon naught, multiply by 2 upon epsilon r plus 1. Suppose epsilon r is 3.2. So now just you put 3.2 here. Frequency or suppose 28 gigahertz. So now here you put 28 gigahertz. Then you can easily calculate the W. After getting this, we have to calculate the length. But now in case of the length, I have already told, now there is a this microstrip patch having a 2 slots, radiating slot. One is this side, another is in this side. So now here in this diagram, once again, I saw that, yes, this is the radiating slot 1, this is radiating slot. So now here this electrical, because here the physical length is L. But now due to these electrical lines or due to freezing effects, now this electrical length will be increased. So here increment by the delta L. Either another side is also increment by delta L. So delta L how much? 2 delta L. So now we have to make a correction. So that's why here L is equal to 1 upon 2 FR square root of epsilon R effective mu 0 epsilon 0 minus 2 delta L, because 1 delta L from this side, 1 delta is from this side. It means first we have to calculate the epsilon R effective. Epsilon R effective, because in this is the microstrip structure. In case of a microstrip structure, the electrical field lines passes through the two medium, that is homogeneous structure. So now that's why epsilon R effective we calculate with the help of this formula, that is epsilon R plus 1 by 2 plus epsilon R minus 1 by 2 multiply by 1 plus 12 H upon W power minus half. So W you have already calculated, epsilon R you already know, and height of the substrate is already know, 30 means suppose 0.762 mm. So you can easily calculate the epsilon R effective. After calculating epsilon R effective, W you already know, H already know. So with the help of this formula, we can easily calculate the delta L. So after calculating delta L, now just we put here epsilon R effective here. So then we can easily calculate the L. It means we know the width and length of the microstrip patch antenna. So it's very easy to design 5G antenna. So that's only 1 minute task. Now just you put 28 gigahertz and you design it. Then you will get the length and width of this. Then next step is came, because now here this is a 50 ohm line, so we require a matching transformer, or we may design the insert fit. So depends on our geometry, right? So now here, suppose input impedance of this patch is Z in. Z naught is the your feed line impedance, suppose 50 ohm. So here this is a quarter wave matching transformer. So now here this ZTR will be a square root of Z naught into Z in. Suppose Z in is 200, Z naught is 50, so square root of 50 into 200. So now this will be the value of Z, and length is lambda by 4, right? So before proceed to that, we have to know, so we can easily calculate the ZTR. And then again question is came, so we know the all impedances, this length width we know, this Z we know, this Z naught we know, suppose 50 ohm, this is a 77, suppose 70 ohm, so we know. But now according to that we have to find out the width. So now width can be calculated with the help of this empirical formula. So now here W1 by H equal to at e ki power a 2 divided by e ki power 2a minus 2, right? And this is applicable for when W1 by H is smaller than 2. So here these are the values of the constant. A is equal to Z naught upon 60 square root of epsilon r plus y2 plus epsilon r y2 epsilon r plus 1 multiplied by 0.23 plus 0.11 upon epsilon r. Similarly, B is equal to 377 ohm pi upon 2 Z naught put epsilon r. And Z naught is the system impedance. System impedance is 50 ohm. So now everywhere you will put the 50, then you calculate the N B, then you put the AB here, then you can easily calculate the W1. Similarly, you can also calculate the width of this matching transformer line also. So now it can easily calculate it. Or nowadays, because when I was doing my MTech, on that time there is no software available. So we will have to use these equations with the help of the calculator. We have to put all these and then we have to find out the width. So now it's a take 2 time actually. So after that, then the MATLAB which came. So now the people have put this formula in MATLAB and they try to calculate these things. So then we can just by putting the input, then we can easily calculate. But nowadays, now there are so many simulation software. So now just now you can go in Google and now just you see Microsd line calculator. So now just you put the values and then you can easily calculate the width. So nowadays life is so easy actually. So now here this is one of the example for a 10 gigahertz. But now in case of the 5G antenna, so now just your design frequency will be changed. Nothing will be changed. Now suppose the same substrate, by using the same substrate, now you can design it. So now here I have given an example design frequency by taking 10 gigahertz. So now just you people can do this exercise with the help of 10 gigahertz first. Then you change this frequency to the 28 gigahertz. So once you take the 28 gigahertz, then what happened? Here the length is 8.2, so you will get the length is 4 mm to mm. The width is again small. So now these value will be very small. Nothing will change. So now here these are so many after calculating this length, width and all these, you know the structure, you know the dimension of that. So then this same, by using the dimensions and all these, we have to put into the software, simulation softwares. So commercially available tool, there are so many CAD simulation software is available. So HFSS, Momentum, Sonnet, CST, Microsd, i3D, and Soft Designer, Empire. Large number of softwares comes, or I think every year there is we know the one new name of the simulation softwares, right? So whatever software is available, up to you, and with the help of that, now just you simulate this structure, right? So for simulation procedure, what will be the procedure? First, we have to define the structure. Then we have to define the ports, then define materials, then define the units and frequency band, define boundary conditions, then set the output parameters. Earlier, I have discussed so many circuit quantities and all these about the antenna. So you have to, because whatever the what type of output we require. So according to that, we have to give the parameter. I need return loss, I need the transmission loss, I need a far field radiation pattern, surface current, E field, S field. So now we have to put the directivity, efficiency, and all these. So according to that, our CAD simulations will give a output results to you. So here this is the procedure. So structure in 3D EM simulator, the same structure is, so this is the simulation window. So now here we have to design the same structure here. Then we have to put the button of the simulation. So now the simulation is start, and the here I choose a return loss as parameters page and our 3D radiation pattern, 2D radiation pattern. So now here these are the results. So now here this antenna is working on 10 gigahertz. So now here this is the S parameters, and this is a 3D radiation pattern. This is a 2D radiation pattern. So now here this is another quasi TM mode, line impedance is 50 ohm. So now here these simulations give so many informations. Why I have shown here? Because now here this is a type is A field, mode is quasi TM. We have already discussed accuracy, beta, your wave impedance. I have already told now 120 to 77.5 ohm, right? So line impedance is 50. So now the most of the information you will get with the help of the software. Similarly, current density, voltage, and all these. So these information. So now here this just I was showing is slightly different actually. I want to design antenna on 10 gigahertz, but now here in this insect feed, this antenna is working on the 9.9 gigahertz. It means what I have to do? I have to do the optimization by changing their length, width, and insect feed and all these. So by changing that, so just I have to reach to the 10 gigahertz. Earlier when these softwares was not available, then what happened actually? Now just with the help of the pen and pencil and calculators, now just we calculate the dimensions. Then we go for a photolithography process and fabricate the antenna. But what happened? When we test that, the antenna is working on 10.2 gigahertz, 9.8 gigahertz. Then again we reiterate another dimension by making small corrections. We again fabricate. So large number of substrate is wastage actually. Huge material wastage. Because one of the my colleague that's designing on 35 gigahertz on that time. Microsd antenna. I think he has fabricated more than 100 antennas, but he never reached to the 35 gigahertz. So wastage so many substrate, right? And substrate is very costly affair. But nowadays, now there is a simulation is there. So now just use the optimized tool and all these, and now you go for the exact frequency. When your exact result is came, then you go for fabrication. That's why this I'm showing this result. So now here these are the radiation patterns. So now here the frequencies and main lobe magnitude and all these, most of the information you will get. Otherwise, you have to calculate by the. So this is the radiation pattern, another far field radiation pattern, because there is a two kind of radiation pattern. So here this after that there is a fabrication. So make the drawing into the AutoCAD or any available software, because we have to prepare the mask. So make the mask using the available sources, print the antenna using the well-known photolithography technique. So here this is the actual photograph of the Microsd. So now here the connector we have connected. So most of the time the people connect the local connector. So local connector is a very lossy. So now first you have to measure the losses, because now here we are designing the 5G antenna, right? So now the such kind of connector cannot be used for the 35 gigahertz and above, right? So here, so you have to choose this connector B specifically. Otherwise, your antenna design is okay, but connector is not okay, then you will not get a good result. So each and everything play a very important role in a designing of the antenna. So here, this is the quarter wave impedance matching transformer antenna is there. So here, this is another insect feed microstrip antenna. This is the actual fabricated antenna. And after fabrication, so we have to go for a characterization. Characterization means now there is a measurement is there. So first we have to measure the return loss. That is the S11, because the antenna is a single port device. If you want to design a filter, the filter will be a two port. So this is a microstrip antenna. So single port device is there. So first we will measure the return loss. Return loss, if the below 10 dB, then we say now our antenna design is okay, right? If the minus 20 dB, very good. And if minus 30 dB, then we say now it's excellent. So now here the return loss says now the how much power is reflected back and how much is transmitted. But I have already told you, sometimes this antenna is absorb the power, because it will not radiate into the space, because if the radiation is not matched to the free space impedance, then it will absorb the power in antenna itself. So that's why the radiation pattern measurement is important. So then we measure the radiation pattern measurement in NQX chamber. So already we have in our laboratory, in our RTU campus, we have recently installed this NQX chamber, and we have a 40 gigahertz NQX chamber. So you want to do the testing and all these, then you come to our campus. So another is the gain measurement. So gain is the very important parameter. So we can measure the gain. So here the by NQX chamber and all these, we measure the radiation pattern. So this will be a radiation pattern. So these are the measurement facilities at RTU. So our affiliated college or any other college or any other researchers can come to our campus by contacting me or any other faculty members. So now you can test it. So these are the some photographs of the devices. So this is the signal generator. This is the VNA. This is the VNA and all these spectrum analyzer and all these devices are there. So this is the NQX chamber. Actual photograph of our NQX chamber. So this is a very big size NQX chamber is there. So now here you see this is the patch antenna here, and now here the thing at the receiving side, now there is a pyramidal horn is there actually, Langrad horn is there. So that's why this horn antenna is very important. I have told you. So here just by putting this trace antenna here, and now just you close the chamber and automatically it will radiate, and now it give the radiation patterns. So now nowadays life is very easy. Earlier when I was doing my MTech and all these, now manually we have to rotate 10 degree, 20 degree, 30 degree. Then we have to measure the power, and then we have to calculate. Then we have to plot the radiation patterns. It takes time actually. But nowadays, now the everything is integrated beautifully. So now here just you put the devices, and now just you measure it. So now here these are the parameter measurement, magnitude of reflection coefficient in a network analyzer. So this is the screenshot of that. So here the frequency is given and all this information you will get. So radiation pattern. So here a mathematically function of a graphical representation of a radiation property of the antenna as a function of a space coordinate. So here why I am showing you, because antenna is radiating reactive near field, radiating near field, then radiating far field. So when you design the antenna and go for a testing, then what you have to do? Because this antenna will be tested in the far field. And what is the condition of that? The condition for the far field should be a 2d square by lambda, right? So now here this is the minimum distance between the transmitter and receiver, and D is the, in the far field of an antenna, the radiating field can be treated as a local plane waves emerging from an emerging phase center. Advantage of a plane wave treatment: so there exists only transversal field component E and H are orthogonal to each other and in phase, right? Phase impedance I have already told you, 125, 377. So this is the minimum distance for the far field. Because our antenna size becomes so small, so now definitely we have to adjust the distance between them. Here now you are looking that na, this is the transmitting, this is receiving. So here we have to place this distance should be minimized. Now suppose we are designing 4G, 3G antenna, right? Because antenna very small. So here the radiation pattern is a graphical representation of a radiation properties of antenna depicted as a two-dimensional cross section, and we have to measure the beam width. Half power beam width is one of a measure of a directivity of the antenna. In the reception pattern, the receiving antenna equivalent to a radiation pattern. So far field of an undistributed patch antenna. These are the mathematical formula. So now here earlier we have to use these formulas. And by wearing this theta 5 degree, 10 degree, we have to theoretical calculations. So you have to think how much difficult. We have to calculate the E and H parameters in every degree, 5 degree, 10 degree, 20 degree. So now that will be a theoretical radiation pattern. Then we have to measure parameters. Then we have to compare them, right? But nowadays, now just we compare the simulation radiation pattern to a measured parameters. So simulation give a direct result and measured give you direct result. So now here E and H refer to the elevation and E plane, H plane. So you already know elevation and horizontal planes for a linearly polarized patch antenna. So here this is the main lobe, back lobe, and a main lobe beam width we have to calculate. So horizontal and vertical antenna. Then antenna gain, the power output in a particular direction compared to the produce in any direction by a perfect omnidirection antenna. So this is the effective area related to physical size and shape of the antenna. So antenna type selection, so depends on the application. Now suppose here we are designing for 5G. So 5G antenna is there, easy of integration with feed network, what type of a feed network we have to design, single resonance or multi-resonance, narrow or wide band, UWB antenna, low frequency versus high frequency, available technology, integration level, cost, size, performance, power level, and reconfigurable antenna. So now here the challenges for the 5G services, because this basic antenna first we have to design. And now you choose the 5G frequency, whatever you needed, 28, 38, 35, or 5 gigahertz. Then you change accordingly and then design the another antenna. So 5G service and scenario requirement, massive growth in mobile data demands, higher data rate, a massive growth of connected devices, low latency for real-time connection, high energy efficiency for longer, better life, new use cases like connected car, machine to machine. So now here the key solution by increasing the spectrum, 700 megahertz, 3.5 or 26 to 28 gigahertz. So now here just capacity will be very high. Ultra dense network, massive MIMO antenna for beam forming and special. So 5G accelerating growth in driving the need for all bands of implement 5G. So 5G multi-band, ultra wideband, and massive MIMO are used for the 5G network. So in a recent year, lot of 5G antenna is designed and different. So here these are the 5G antenna classification. Just a minute. So sorry for interruption. So now here there is a 5G classification based on the input and output ports. So here the 5G antenna can be classified into the single input, single output, multi input, multi output. Similarly, there may be a wideband, may be a multi-band. There may be a single element, multi element. So now here this is a bigger classification of that. So now here single input, single output. So here the short form is CISO. CISO antenna is easy to design and implement. Single antenna, just like the just I shown the microstrip antenna, it can be easily integrated into the 5G communication devices to achieve a high gain and size of a single element antenna is a large. Above 6 gigahertz frequency band, signal suffers from higher propagation, losses and quality of service. Similarly, the multi-input and multi-output. So the wireless communication is prone to interface, multipath fading and radiation losses. It becomes severe at higher frequencies. Overcome these issues, utilizes of a multi-input, multi-output antennas becomes very important as it enhances the transmission range without increasing the signal power. MIMO antenna can be useful in a 5G to achieve a low latency, maximum throughput, and large efficiency. In a MIMO, more signal can be launched intelligently by using multiple antenna and thus enhancing the channel capacity. Another method used to reduce the number of antennas in a MIMO is to use multi-band antenna. Either we have to use a multiple antenna or we use the multi-band antenna, because in our mobile also we have a 2G, 3G, 4G, Bluetooth, Wi-Fi. There are so many things is available. So many communication is available in our mobile. But now we are using only one antenna. So maybe a reconfigurable, maybe a multi-band antenna. So in the MIMO antenna can be classified depending upon their frequency band as a wideband and multiband. We may use a wideband. Now suppose from 1 to 5 gigahertz, or we use a multiband antenna. So different type of enhancement techniques are used in various antenna structures to increase the gain, improve isolations, among the antennas, bandwidth, envelope, correlation coefficient. It's very important in MIMO antenna and efficiency. So the classification based on the types of the antenna. So various types, you can design any antenna. Monopole, dipole antenna, magneto-electric dipole antenna, loop antenna, antipodal Vivaldi antenna, fractal antenna, inverted F, planar inverted F. So all these antenna used in our mobile actually, right? So when you open your mobile, so then definitely you will see these antenna inside the mobile, right? So now here they have a certain advantage and disadvantage because antenna is a huge field actually. So now here the monopole have a certain advantage, simple to design and fabricate. In a multi-element monopole antenna design, it can be easily rotated in any direction. It has a disadvantage also, less gain, require large area of ground, gives a poor response in a bad weather condition. Similarly, dipole, simple to design and fabricate, receive the balanced signals. Disadvantage is a less gain, cannot be used for long range communication, low bandwidth. Magneto-electric dipole, high front to back ratio, low side lobe, back lobe level because we do not require the backside lobe. Na? Otherwise, what happened? Now it create a problem. Wide band and width, low cross polarizations, and disadvantage is design and fabrication is complex, costly. Loop antenna again, easy to design, provide a good channel capacity. Disadvantage as a single element loop antenna cannot meet the 5G requirement. So multi-element loop is a required, low gain. Similarly, Vivaldi antenna enhance the gain, the very popular antenna. Provide the wider bandwidth, give us stable radiation pattern, require more space, low gain and lower efficiency. Similarly, fractal antenna, it help a miniaturize the antenna size, provide wider bandwidth, good impedance matching, provide consistent antenna performance over the operating range. And here the disadvantage, design is complex, limitations on a reputation of fractal design. Inverted F is smaller in size, good impedance matching, and but now problem created with the narrow band and low gain. Similarly, the planar inverted F, low profile, good impedance matching, but now there is a disadvantage is narrow band and low gain. So now here again with the by merits and demerits, we have to choose the what type of the antenna will be suitable for my system. So first you have to choose that whether we have to design Vivaldi, we have to design the loop and whatever. Then come to the point of the substrate choice. The main requirement of antenna implement is we have already discussed selection of the substrate to increase the gain and reduce the power level. A substrate with the less relative permittivity and low loss tangent must be selected. Another is the corrugation. Corrugation means removal of metal part from the edge of the radiator. It helps to improve the bandwidth and front to back ratio. Similarly, multi-element, the gain of antenna can be increased by the multi-element antenna because one antenna is not sufficient to transmit. So now we use the more than. It also enhances the antenna bandwidth and the efficiency. Another is the dielectric lens. So electrostatic radiation is a transmission in one direction by a dielectric lens which lead to increase in gain and directivity of antenna. Just like a lens, na? So now just they improve their directivity. Mutual coupling reduction technique. So multi-element antenna design, the antenna element affect the performance to each other because they couple to each other. Na? So to reduce this and incorporate different mutual coupling technique in MIMO antenna because this very popular antenna nowadays people are designing for the 5G network MIMO antenna, which is also named as a isolation or decoupling technique in the literature. So now here there is a mutual coupling reduction technique. So these techniques are an avoidable part of a MIMO antenna design. That is a neutralization line using metallic slit or lumped element neutralization line passes electromagnetic wave between antenna element to reduce the mutual coupling. It reduces the antenna area and improve the bandwidth when connected between the ground and plane. Similarly, there is a decoupling network. In the decoupling network, cross admittance get transformed to purely imaginary value by adding discrete component to transmission line. These techniques employ a plane decoupling network which act as a resonator to reduce the mutual coupling. Similarly, EVG structure. So EVG structure is made of the dielectric or metallic material having a periodic arrangement. So EVG structure provide a low mutual coupling and high efficiency. So EVG antenna, DGS antenna, dielectric resonators, and in case of a dielectric resonator, an antenna that contain dielectric resonator is called a DRA. DRA provide a high gain, high radiation efficiency, and low loss. DRA can also provide a high isolation with the dual band properties. DGS antenna, defective ground structures. So it is the structure where the slot of defected constellation on ground plane of antenna. So DGS can be used to provide maximum efficiency, low mutual coupling, and wide bandwidth. So now suppose we have to increase the bandwidth, then we have to use the defective ground structure. Similarly, people are nowadays designing the antennas with the help of metamaterial. So one of my PhD students completed the antenna designing on the metamaterial. It contains electromagnetic characteristics, different type of the metamaterial, are a single negative electromagnetic bandwidth, band gap, double negative and isotropic terahertz, chiral and tunable photonic frequency selective surface based, non-linear and tunable metamaterial. Metamaterial are designed manually by using two or more material. Using metamaterial, it is possible to have an antenna with low mutual coupling, high gain bandwidth, and compact size of the slot element. I have already shown you the slot line. So now it is used to enhance the impedance bandwidth using the coupling method in the ground plane or radiating patch. The slot antenna is used to provide wide bandwidth, high gain, high efficiency, and high mutual coupling. Complementary split ring resonator CSRR used for the isolation improvement are also used to provide high efficiency and made up to the concentric ring structure with slot opposite to each other. Frequency reconfigurable. So now reconfigurable means the same antenna can be used for the different by using the switches. So it is based on the switching technique in reconfigurable antenna to increase the frequency range or to increase the envelope correlation coefficient. Varactor diode, MEMS switches and pin diode are used. Why frequency reconfigurable? Because the same structure can be used for the 4G, 5G because we have to integrate the whole systems. So the reconfigurable antenna structure can provide a lower mutual coupling, a high value of diversity gain and efficiency. So here this is the CISO wideband antenna designing. So this is a multi-layer antenna designing. So these antenna are either of a single element or multi-element. So CISO antenna for 5G application can be categorized into single element and multi-element. So here by using this meta surface, the people have designed this antenna. So this is a return loss, this is a gain and acceleration. Similarly, this is a multi-element antenna. The picture is shown here. It provides the most important requirement for 5G antenna as a high gain and stable radiation pattern and wider frequency band. So now here this is the return loss. So we can see this is from 25 gigahertz to the 40 gigahertz. This is the gain of that antenna. Similarly, CISO multiband, single input, single output, multiband antenna can also be classified as a single and multi-element antenna. It provides less gain and bandwidth. So this is a MIMO wideband antenna can also be categorized as a multi-element without a metal rim, multi-element with a metal rim. So this is the fabricated structure. These are the result of the 5G antenna. So this is the MIMO wideband antennas. So many people have designed different type of the antenna, fabricated multi-element antenna with the performance characteristics. There's the return loss measurement of this. So here this is the another antenna where the four antennas are used, antenna 1, antenna 2, they are placed different places, right? So these are the return loss and isolations because they should be isolated to each other. So multi-element without metal rim antenna. So this is another structure and these are the race parameters results of these antennas. So multi-element antenna without metal rim, multi-band element antenna is a panacea of the rapid development of wireless communication with demands heterogeneous network simulation, access to or more technology like Wi-Fi, GSM, Bluetooth, 4G, 5G, because we have to integrate all these. So this antenna cover GSM, LTE and UMTS applications with a good isolation and better efficiency for a both lower and higher efficiency band. So here we have a different antennas, multi-band antenna, 10 antennas. The people have designed this and these are the result of that. So multi-element with a metal rim antenna. So here this again used for the mobile. So demand for multi-band metal rim antenna. So this is the result as parameters and all these. So here the application, the 5G technology in a mobile communication is energy efficient and offer high throughput, low latency, increases scalability and reliability. Also the key technologies such as cloud-based radio access network, massive MIMO, device to device communication network densification because we have to place these antennas within 100 feet or 100 meter. Virtualization of a resource play a vital role in fulfilling the requirement of 5G. So now here in smart antenna, in smartphone, the antenna category will be a MIMO with multi-mode loop, monopole antenna, IF antenna. Technology will be a beamforming, carrier aggregations, multi-antenna technology. Base station design will be different. The base station and mobile terminal. So antenna will be again MIMO element antenna with DGS, M MIMO antenna with a switched beam steering technology will be a multiple antenna technology, millimeter wave radio access network, and cell free and MIMO. 5G IoT, because all will be integrated to each other. So antenna category will be a UWB monopole, because we have to cover very wide bandwidth. Phase a multi-element antenna with beamforming network, massive MIMO. Technology will be a centralized RAN, software-defined wireless sensor networking, and a network function virtualization and commutative radio. So when we know the each and everything, then we can integrate all them, and then we design. Then we can design a 5G network. So now here this is another 5G antenna, very simple antenna. People have designed that on the 28 gigahertz. So now just you can choose any structures, and by using that step, so now just you fabricate it and simulate. This is the multi-band antenna for 5G. This is another antenna. This is the using MEMS. MEMS means micro electromechanical system. So the people are using the reconfigurable antenna using a pin device. So now the device design technology remains the same. Only thing is that now you have to change your specifications. So 5G specification is different and 4G specification is different. So this is another compact design for a future millimeter wave 5G smartphone. So this is a smartphone antenna, planar array operating at 28 gigahertz. Corner is the band and radiation pattern of the corner band array in HDNA plane at 28 gigahertz. So this is another planar printed Yagi antenna. This is the result. So this is the another antenna, compact printed Yagi Uda. Same antenna used for the smartphones. So these are the radiation patterns and all these. So this is about the 5G antenna. I think more than time I have consumed. So now, thank you. So thanks.
Thank you, sir. Thank you very much, sir. Now all participants are requested to ask their queries. If they have any query, ask them, sir.
So if they can have another query, they can mail me also. So
Yes,
if they
sir.
on mail, so now just you can share them my mobile number and other. If anybody is needed any help in fabrication and other things, then you can share
Yes,
them.
sir.
So thank you.
Thank you, sir. So now all participants are requested that switch on your camera for a group photograph. Thank you, everyone. Thank you all. Thank you very much, sir, for the
Thank
nice
you.
session.
Thank you. Have a nice day.
Yeah.
Thank you.
Thank you, sir.
Okay, thank you.
Thank you, sir.
The next session will be at 11:30 a.m. Thank